Welcome to a lesson with Dr. Powell. Let's look at how we can find the surface area of a rotated solid or a solid formed by rotating a region. So by surface area, we mean kind of the lateral outside area that happens in the rotation itself. So if we take like the curve y equals square root of x from the x on the x-interval from 0 to 1, we rotate it about the x-axis, spinning it around, get a shape that looks something like this. I'd like to know what that surface area is. Well, first we need to find the surface area derivative with respect to growth by x along the axis of rotation. Okay, so let's look at a little picture here, just of like increasing surface area along this function as we go along this way, and look at a little change of a, because kind of that's what we're after. We want kind of know what change of a over change of x is. If we take this strip, which we've kind of outlined right here, and we unravel it like so, notice that the distance across the strip is simply just the arc length right here. It's been rotated around. But on the ends, it's going to be kind of jagged or funny or whatever else it'll be. But one thing we know for sure that the side lengths are kind of in between what they would be, what the kind of the smaller circumference is versus the larger circumference. Larger circumference over here and the smaller circumference over here in the rotation itself along the edges of the strip. Well, the larger, and as change of x gets smaller and smaller, these two circumferences kind of converge to be about the same. So in particular, this is what we're looking at. The derivative of the surface area with respect to x, so with respect to axial growth, can be thought of as the circumference at a particular position, x, but which we write as 2 pi r. Now this r is going to be, at least in this particular case, is going to be the y value of the curve, so square root of x. But I'll just leave it right here because you'll have to interpret it per situation, times the square root of 1 plus the derivative with respect to x of the curve squared. And why is that? Because this right here is the derivative of arc length, and it represents the so this right here represents the ratio of change of s to change of x, but really ds dx. So this is ds dx. This is and we're taking that, and so think about it, you kind of have circumference. So it's like you have circumference 2 pi r times change of s. So that kind of gives you this area right here, which is this is the change of a, right? This area right here, and then you take that change of a and divide it by change of x, but we're putting it right here with the change of s. So we can write this out as the arc length derivative right here. So using that idea, let's look at an example, the specific example. So this derivative at a particular value of x, just along here, any arbitrary value of x as we move from 0 to 1, the radius will be square root of x with this particular curve. And then we need to take a derivative of root x to be 1 over 2 root x. So it's 1/2 times x to the negative half. And we're squaring that. Now squaring this is just 1 over 4x. So it's 1 plus 1 over 4x. But upon adding fractions, that looks like this one can be thought of as 4x over 4x. And you have a 4x in the denominator. It looks something like this when you add fractions. And so this is the next step where I've distributed the square root across the division here, or the fraction. And then notice that 2 root x is the same thing as square root of 4x. So those cancel out. So you basically just left with pi times the square root of 4x plus 1. Take an antiderivative. You could use a u substitution or just thoughtfulness. And I kept the same bounds because I kept everything in terms of x, and you can double check that the derivative of this is that. Basically a simple u substitution, because the derivative of u would be 4. So really the result is like a division by 4 here extra. Then it's just the 2/3 times the thing to the 3/2 power. And you're plugging in 0 and 1. And when you do that, and in simplification, factoring out, you end up getting this right here. So this is a measure of the surface area formed when upon that rotation. Thanks for watching.